Okay, moving on, doing some review here. All right, operational definition. Basically, it tells you how to do something instead of just defining it. The example that I use is blowing my nose because I have allergies, so I do that a lot. Definition is like forcing air through your nose to rid it of unwanted debris. The operational definition would be more like, well, use a tissue, force the air from your lungs into your nose, and then into the tissue, discard the tissue, and finish. So an operational definition is more like a recipe. It's a very detailed definition and not just the very basics. Think of it that way at least. So, you will have something about an operational definition on your final, so know that. Properties. Different types of properties. An intrinsic property is a property of the object itself. If it changes, the object itself changes. Intrinsic properties include things like, I can write these out here because I can. For example, it would be mass, volume, volume, density could be intrinsic property. Basically, the object is not the same that it was before. And I wrote some there. I feel stupid. Anyways, so those are your intrinsic properties. Your extrinsic properties are things like location, temperature, weight. Those are things where the object itself doesn't change, yet it's still a property about it. And so that's the kind of the key here. It's similar to extensive and intensive properties that you learn about in chemistry, or they're taught now in high school chemistry, or I guess they are taught now. A little bit different. It's just kind of a classification system. I've thought about switching over to extensive and intensive. I just haven't got around to it yet. Lots of things to do. Anywho, characteristic properties. It's the same for all objects made from the same material, such as density, binding energy, other example, specific heat, conductivity. Trying to think of things we went over, but I didn't really go over conductivity. But anyways, you kind of get the picture. It's the same for all objects, no matter the mass and volume. So, well, speaking of volume and mass, volume and mass. Volume is the measure of how much space an object displaces. Basically, it's length times width times height. For a cylinder, it's pi r squared h. For a cone, it's 1/3 pi r cubed, and so forth. It's always going to have three dimensions to be volume. R is your 2 squared, so that's your 2 dimensions, and then h is your 3rd dimension. In this case, it's just solely dependent upon the radius, and that's the cube. So it's always going to have 3 dimensions for volume. Mass is the measure of how much matter is in an object, not to be confused with weight. Weight, if you recall, depends on the gravity. And the example that I used for this was, you have mass no matter where you go. You have mass here, you have mass on the International Space Station. You can't step on a scale in the International Space Station, but you still have mass because you still exist. And so weight depends on the strength of the gravitational field at that location. And if you recall, you would use an inertial balance to actually find your weight if you were on the International Space Station. So, you will, I think, have at least one question that deals with volume and mass. Yeah. And you're also going to have a question that deals with maximum deviation. Errors are encountered in your lab work. To find your error, you first throw out any outliers. They will be obvious. Then you're going to find the average of at least 8 values. You need 8 to kind of have a decent statistical spread. Not always. It's kind of just a short guess, but it mostly works. Find the second largest value, subtract the average from it. Find the second smallest value, subtract the average from it. Use the largest of the error. Now, if this is density or anything that's 2-dimensional, you would actually use, well, let's just say density for this time, because you're not going to have anything else but density on the final if that happens. You would use the largest of the two. So that's kind of your difference there. Meaning you're not your second largest, but your actual largest value from each one. And then you write it as x plus or minus y. So I will do an example. We have 10, 10, 15, 20, 5, 5, 10, 10K, so quite low Kelvin values. We have lots of 5s, some 10s, 115, and then 120. This 20 is just too high, so I'm going to get rid of it, and that still leaves me with 8 values. And so what I need to do is just find the average, and so I just take 10 Kelvin plus 10 Kelvin plus 15 Kelvin plus 3 times 5 Kelvin, save me a little bit of writing space, plus 2 times 10 Kelvin, and then use the little blue. I don't know what that is, but I just made it up. And then you divide that by 8 to get your average, and I actually wrote down the values this time because I have a lot of these to do. And that's going to give you 8.75 Kelvin. So then you take the second largest and the second smallest. They can be repeated values. So with largest, it goes 1510. So then the large is going to be 10 minus 8.75, which is going to give you 1.25 Kelvin. And then for your small, put SM for small, it's going to be 5, 5. So 8.75 minus 5 is going to be 3.75 Kelvin. And so remember, you write it as mu plus or minus sigma. So mu being your average, sigma being your, it's more or less your standard deviation. So then I write it as, okay, 8.75 plus or minus 3.75 Kelvin. And that that plus or minus 3.75 says you got quite a lot of variation relative to your actual value. It means it could be as high as 12 and a half or as low as 5 is where you expect to find your values. And so that's probably a pretty high error. Basically, it usually is an indication that your measuring device or even your process wasn't quite on par. An example would be measuring the mass of a paperclip, and you only have the precision of getting it out in grams. And so, yeah, you're going to have nearly 100% error, just because your equipment's not quite accurate. I'm sorry, enough. So, you'll have one problem on that, so make sure you know how to do that. Graphing. You're going to have something where you have to graph. When graphing, be sure to use a straight line if it's linear. And you label all your axes. And so in this case, you make sure you have to have a title. And your title should, it's not 100%, but it should always be whatever your y value is versus whatever your x value is. And then that y is what you put over here, and your x is what you put over here. So if this is distance and time, this would be distance versus time. So make sure you do that, and make sure you put units. So this would be meters probably, and this would, oh, sorry. This would, yeah, that would be meters, and then this would be seconds, probably. So, yeah, you're going to have at least one graph. And when you do use the trend line in order to interpolate or extrapolate numbers, make sure you actually use the trend line and not the individual data points. In this case, it lines up perfectly, but sometimes you may have a point here, point here, point here, point here. It's just this kind of just bisects the most points as possible. You'll have at least one on density. Density is the mass divided by volume. By the way, there's lots of different densities. This is actually called mass density. There is an area density. It's not in this physics class. You do it a little bit if you take physics 213. Area densities, you do that if you take physics 313, 314. But this is a mass density. If the density is less than the density of water, it floats, whatever object that is. And then the density is greater than the density of water, it sinks. Sometimes you can have varying densities. This is a picture of white grape juice. I forgot to put words from, but oh well. White grape juice, orange juice, and pomegranate juice. So the most dense would be on the bottom, the least dense would be up top. So your pomegranate juice would have the least amount of density, followed by orange juice, followed by white grape juice. So this also leads to a apparent weight, if you recall. Apparent weight. And basically, the apparent weight is what you would weigh on a scale in that fluid. What you weigh on scale in fluid. And so apparent weight, the less dense your liquid is or fluid is, the higher your apparent weight. So air is a fluid, and it's very, very, very has a very, very, very small density. So your apparent weight is highest there. Your apparent weight would be highest in pomegranate juice, and lowest in white grape juice. So, just in case you want to weigh yourself in juices, I don't recommend it because, yeah, it just doesn't seem very fun. Anywho, coordinates of location. Coordinates are important as it tells you where one object is relative to everything else. For example, you describe most distances with your house, place of work, or WSU as your place of origin. Especially if you're looking up how long is it going to take to get to Kingman. Why would you want to go to Kingman? I don't know. I was just on the top of my head because Kingman County has not got a single case yet of coronavirus, which I kind of find fascinating. Well, if you want to figure out how to go there, your place of residence would probably be your origin in that case. Another thing is displacement and position and distance. Your displacement is how far you travel overall from point A to point B. So let's just say I take point A and then too far down. There you go. Point A and point B. Your displacement would be this. Displacement is two things. It has magnitude and direction. And so displacement would be from point A to point B, but it has to have direction. Your distance, on the other hand, does not have to have direction, and it can take into account a varying of different ways of getting there. And that is the difference, and that would be your distance that you traveled. Relatably, you have speed, and then you have velocity. Speed is distance over time, whereas velocity is displacement over time. And remember, your speed is always a positive quantity, whereas your velocity can be positive or negative. And so, know those things. You may have at least one of those things pop up in your test, or final in that case. All right, on to velocity and acceleration. I've already mentioned it before, but velocity is the change in position over the change in time. Your basic equation is v is equal to delta x over delta t, and the equation that I normally use is like a v average times delta t is equal to delta x. This is basically your rate times time is equal to distance equation that you may have learned in algebra in high school, just with different variables. And that's not really an equation. All of it is just based off of the definition of velocity. Acceleration is the change in velocity over change in time. So you say A is delta V over delta T. I usually rewrite that as VF is equal to VI plus A delta T. It's not a special equation. It's just based off the definition of acceleration and rearranging some variables. But this does give you your final speed in relation to your initial speed, the acceleration, and the time. So we will use these things in a problem. You're not going to have a problem this long. I just try to cover everything. It may be about 2, maybe 3 parts. I think it's only 2. But I want to make sure I try to cover at least a decent chunk of what you might see. So, I found a picture of an SUV that looked funny, so here we go. SUV is traveling at 10 meters a second, speeds up to 20 meters a second after 20 seconds has passed. It helps to kind of draw a picture out, and so I know that it starts and it takes 20 seconds. Ooh, that's not good. Let's do this. Ha ha ha. It starts and then it takes about 20 seconds to get to 20 meters a second. It travels at the speed for 10 seconds. So it's saying it's going at a constant speed. So I'm going to draw it slightly smaller, maybe roughly half the size. And then over the last 10 seconds, it slows down to rest. So then one more, roughly the same size as the last one. All right. So then I know that this took 20 seconds. I know this took 10 seconds, and I know this took 10 seconds. I know at the end the speed is 0 meters a second. I know at the beginning the speed is 10 meters a second. That doesn't look very good. I know what you were thinking. Okay, maybe you weren't thinking that, but I certainly was. And then at this point right here, this is 20. And remember, it holds that speed, so this is also 20. So, now that I have it kind of written out, basically you could think of the speeds aren't quite accurate on this, but let's say you get off on K96. No. On I-235 up on the northern side of Wichita, and you then speed up until you get into the K96 exit. Well, no, sorry. You speed up till you get to a constant speed, and then you hold that on cruise control, and then you have to slow down when you hit to the K96 exit. And sometimes you have to stop on that bridge because there's always wrecks. So, anywho, well, what is the acceleration in the first 20 seconds? Different ways of doing this, but I generally will use the fact that Vf is equal to Vi plus A delta t. I know my final speed is 20, and I know that my initial speed is going to be 10. I don't know my acceleration, and I do know the duration is 10 seconds. I end up getting... I take my speed 20 minus 10 is going to give me 10, and then I divide that by my 10 seconds, and I get 1 meter a second squared. Okay, 20 seconds. Dang it. I just realized I made a mistake. My bad. You're probably like, why did he just do that? And I was thinking the same thing, like, that didn't make sense. There we go. It should be 0.0, 0.5. My bad. Okay, 0.5 meters per second squared is my acceleration. Okay, so now that I have that, I can answer the second part. And how far did it travel during that time? I will always use the delta x equation equals Vi delta t plus a half of A delta t squared. It's not the only one, it's just the one I normally pick. There are more ways of doing this than I mentioned, but I can use it and get my answer all the same, so I'm going to do that. So I take my initial speed of 10 times 20 seconds plus 1/2 of my acceleration, which was 0.5 meters per second squared, and then 20 seconds squared. Remember, your time is the only thing that's squared. That gives you seconds squared, which cancels out with this second squared, leaving you a unit of meters, which is what you want. Once you solve this, you should get 300 meters. So, 300 meters. Then it says, okay, well, how far did it travel in the period 20 to 30 seconds? So from here to here. Well, it had a constant speed, so I need to use the fact that delta x is equal to V average delta t. Could I use this equation again? Yeah, I could. It'll give you the exact same thing. Your initial velocity, in that case, would be 20 meters a second. Your acceleration would be 0, and you literally get the exact same thing, x equals vt. It's just more convenient to write this out here. So, okay, well then delta x is equal to 20 meters a second times 10 seconds it occurred for, and that's going to be 200 meters traveled. Okay, then it says what was the acceleration during the last 10 seconds? Once again, I'm going to use my VF equation to find the acceleration. Not the only way, but I believe it's the easiest. Because I know my final speed is 0. I know my initial speed is going to be 20. And my acceleration is what I'm looking for, but my time is a 10 seconds. So it's going to give me negative 20 over 10. My acceleration is going to be negative 2 meters per second squared. Okay, so now that I know how much it accelerated for, I need to find how far the car traveled. Different ways you can do that, but I tend to like to use the delta x equation that I used earlier. I think it's the easiest one to do, so I will. Alright, well my initial speed was a 20. It took 10 seconds. Then plus a negative 2 meters a second squared times 10 seconds squared. And so when you do this part right here, that's going to give you a positive 200. Forgot a half here, totally. My bad. Hopefully I said it and just forgot to write it. Let me fix that real fast. Plus 1/2 of a negative. There we go. So I take 1/2 of the negative 2. That's going to give me a negative 1. Negative 1 times 100 is going to give me negative 100. So you could think of it as your positive forward velocity is going to give you 200 meters, but your acceleration vector is going to take away 100 meters, and that's going to give you an overall displacement of 100 meters, which makes sense. I mean, when you slam on the brakes, you're still going forward, so you're still going to have a positive displacement. In this case, 100 meters. So you will have, like I said, one question that has like 2 parts dealing with kinematics. Okay. Oh, I've left my entire page to work on there. Oh well, that's fine. All right. Another type of kinematics problems involve free fall, and for some reason I found this one day on Amazon, and so I did a problem about it. So we have a child in a mop outfit. Is tossed into the air at 10 meters a second, directly up from an initial height of 1/2 meter. Think of like a father throwing up their child. I guess maybe a little bit older than that kid, but you get the picture. I just think it's funny because he just calls around and cleans the floor. Anyways, how far is the ground off the ground is the child at 1/2 second? What is the speed of the child at 1.1 seconds? And how high does the child travel? Okay, a couple different ways here. Now remember, anytime you are in free fall, your acceleration is going to be negative 9.8 meters per second squared. It says the initial velocity in this case is going to be 10 meters a second. So we also know that. We know the initial height is a 1/2 meter, so I will need to factor that in here in a moment. So let's first figure out how far off the ground is the child at 1/2 second. The easiest equation to use would be your delta x is equal to oh wow, that's bad. Let's try this one more time. Vi delta t plus a 1/2 of a delta t squared, because we know the time and we know the initial velocity and we're looking for delta x. So let's do that. Delta x is equal to Vi would be 10 meters a second times a 1/2 second. Just going to go ahead and put out the minus 1/2 of 9.8 since I know it's going to be negative, times a 1/2 second squared. Solving for this delta x should give you 3.78. Yes, 3.78 meters. And it says how far off the ground, and we know it had initial height of a 1/2 meter. And so that was going to give me 3.78, 0.5, what is that, 4.28. Sounds good. Okay, so yeah, about 17 feet off the ground. I guess they threw the kid a little too hard. Well, let's pretend it's like Tom Brady or something, just throwing a child in the air, and I don't really know. You get the picture. Point is, moving on, sorry. Alright, so we now know the height of the child at a 1/2 second. We need to figure out the speed of the child at 1.1 seconds. So, easiest thing to do here is to use the fact that Vf is equal to Vi plus A delta t. And I want to figure out what the final speed is. I know that my initial speed is going to be 10 meters a second. My acceleration is 9.8. And I know that I wanted it at 1.1 seconds. When I factor that in, I get a, oops, made a little pencil mark. Go away. All right, good. Negative 0.78 meters a second. So it'll be negative. Basically what that tells me is if I have a person, here's my Tom Brady, Tom, and he's a Buccaneer now, and I throw him up from initial height, it's going to tell me that the child is about at this little point right here. It's just starting to fall to the ground. So that's why it's a negative. Okay, so that answers that one. How high does the child travel? Okay, well, this time I need to do two things. I need to first figure out how long it takes to get to the top of this trajectory. I know at the top of the trajectory, the final velocity is going to be 0. So what I want to do is use this final velocity equation, knowing that my final speed is 0, my initial speed is 10, and then minus 9.8 meters a second squared times delta t. Because first I need to figure out how long it takes to get to the top, then I need to use an equation to figure it out. There are other ways of doing this. This is just the way I chose. That gives me 1.02 seconds. So it should take 1.02 seconds for the child to reach the apex of the motion. Well, to figure out the height, I just go back to using the delta x equation, like so. And so, okay, well then delta x is equal to my initial velocity of 10 meters a second, the time of 1.02 seconds, minus the 1/2 of 9.8 meters a second squared, 1.02 seconds quantity squared. This will give me the change in height, and I believe I got 5.3 meters. But recall, that's delta x. The child was initially thrown off the ground roughly a 1/2 meter. So I should add my 1/2 meter to the shebang and say 5.8 meters. So he really chucked that kid pretty high. Probably shouldn't have made the initial velocity so high. But hey, we'll pretend the kid lives. It's Tom Brady. Things always seem to work out for him. Okay. Alright, so we got 5.8 meters, and that is how high the child travels. So there you go. I believe you're going to have one problem that's going to deal with free fall, so just make sure that you remember that acceleration is a negative 9.8. It's always going to be negative because it's always pointing towards the center of the Earth. So, moving on. Graphing. I mentioned you're going to have graphing, and you may have a problem where you have to do some graphing interpretation. This is a distance versus time graph, and so there's a couple things you can get from a distance versus time graph. Let's start with the straight lines. These straight lines are constant speeds because the slope is constant, and since the slope is constant, that means the speed is not changing, because remember that your speed, or in this case velocity, is simply delta y, in this case, over delta x, and if that value is a constant, then you're not going to have any speeding up or slowing down. Now, I put both of them as being at a constant speed. Remember, speed is a positive quantity, so it doesn't matter if it's going down or if the blue guy is going up, it's still going to be constant. Now, it does differ. The blue guy is moving forward while the purple fella is moving backwards because it's going from 20 back towards the origin. Now, the other two, we have slowing down and speeding up. In this case, the slope is changing with time. Anytime the slope changes with time, you have an acceleration. So you can either speed up or slow down. This one in particular is speeding up because the slope is increasingly getting more positive. And this one is slowing down because the overall magnitude of the slope is getting smaller and smaller. And so those are two other things you can glean from this. Okay, now, what about velocity versus time? Well, velocity versus time is a little bit different. This would be a constant speed, meaning your velocity would stay at like a constant 17 meters a second. Um, this would be moving forward because your velocity is increasing with time, and this would be moving backwards because it's decreasing with time. Both instances are speeding up because, um, in which case it doesn't matter whether you're going forward or backwards. Remember, speed is always a positive quantity. So be sure to know these because I think you have one question that may have to deal with this. And the last thing that we did, that we just had a test over, is thermophysics. A couple things to know. You mostly deal with alcohol, and it expands roughly 1% for every 10 degrees Celsius. Not everything is 1% for every 10 degrees Celsius. I'll do a problem with water, which is much less. But all the same, you may have a problem that deals with thermal expansion. Also, conservation of energy, and it states that energy is transferred from one substance to another. And I always keep forgetting to change it. This is like how it divvies this out. Ignore this because it looks like it's a minus. It's not. We'll just put a big dot there and a dot here. How about that? This is saying M1C1 delta T1 is equal to negative M2C2 delta T2. Basically, this is delta E1. This is negative delta E2. I do know that delta E1 plus delta E2 is equal to 0, and so if you move it to the other side, that's where you get the negative. That means that no energy is lost to the environment, like a perfect bomb collimator or something like that. All right, so you'll have at least one problem dealing with that, and I'll do an example, at least a partial example here in a bit. Latent heat of fusion and vaporization is the amount of energy needed to freeze, melt, or vaporize, condense a substance. That's where you have E is equal to MLF, E is equal to MLV. Remember that it's latent, which means that there is no temperature change when this occurs. Latent means without temperature. Basically, the energy needs to go into changing it from one state to the next, instead of heating it up and cooling it down. So I'll do a problem on that in a second, but first let's do thermal expansion. So let's say Loch Ness, assuming it's a cylinder. Loch Ness is in, I believe, it is in Scotland. It's very deep, and it does kind of have somewhat of a cylindrical shape. It's probably more conical, but for the case that we're doing, we're just going to do cylindrical. And so we'll assume it's a cylinder. Its average depth is around 132, and its surface area is around 5.6 times 10 to the 7 meters squared. It's a pretty big lake, by the way, or loch in this case. How much will the water level rise if the temperature goes from 5 to 20? Water expands by roughly 0.1% for every 10 degrees Celsius. It's actually a little bit less than that. So these are reasonable numbers from the winter to the summer, so this is actually somewhat close to being how much it actually expands and contracts or raises up. So we will do we'll figure that out. So, all right, we know it's 0.1% for every 10 degrees Celsius. So that means 0.1% per 10 degrees Celsius. But I need to change that into a decimal form, so it's going to be 0.001 per 10 degrees Celsius. I know that the change in temperature is going to be 15 degrees Celsius. And so when I take my 0.001 by 15, I get 0.0015. Well, sorry, by 15 then divided by 10. That doesn't make much sense if I said it that way. So, 0.0015. This isn't a percent change, but I can figure out how much that's going to act on the actual volume to see the volumetric change. And I will do that in a second, but I need to figure out what the volume is first, because I know the area and I know the depth. I need to figure out the radius anyways, so I think I'll go ahead and get that. This is the surface area, and the area of a circle, if you recall, is pi r squared. So I'm going to go ahead and get the radius because I'm going to need that at some point anyways, at least in my, yeah, more or less need that. So let's go ahead and do that. All right, so that'll be 5.6 times 10 to the 7th square meters is equal to pi r squared. When you solve for r, you're going to get 4222 meters. So that's roughly the radius of Loch Ness. Now, I want to get the total volume, and if you recall, the volume of a cylinder is pi r squared h. Yes, I could have just taken this area and multiplied it by the height, which is exactly what it's going to be, but I'm going to go ahead and write it out for the sake of maybe you don't get it in an area form. So let's do that. So that's pi 4222 meters squared 132 meters, and I get a volume of 7.392 times 10 to the 9th cubic meters. So this change is going to act on that volume to get you a change in volume. So that's what I'm going to do next. 0.0015 times 7.392 times 10 to the 9th cubic meters. And that's going to give me my change in volume, which is going to be 11,088,000. So the change in volume just by thermal expansion of Loch Ness, assumed and with some assumptions there, is somewhere around 11 million. Quite a lot of water change. Now, to figure out how high the water level is going to rise, I know that delta V is equal to pi r squared h. So I could take that, plugging in there, with the radius I know is going to be constant, so we call it the cylinder, and then I could figure out the height. So I'm going to do that right now. So I'll take my 11 million, I'll just say 11.088 times 10 to the 6th cubic meters is equal to pi 4222 squared h. When you solve for h, you won't get a very big value. I mean, it shouldn't be, otherwise we'd probably hear about it. But you do get around 0.2 meters, so that's around 20 centimeters, which is pretty significant. So basically, if you assume that Loch Ness is a cylinder, its water level will change by roughly 20 centimeters from the summer to the winter. Not a lot, but enough that you could actually measure it from the two different times a year on average, assuming that no drought or anything that would change that situation. So, anywho, you may have, I think you may have one thermal expansion question on your final. All right, last one. And you just did this recently on a test, so I'm not going to cover everything, but at least I'll do one part here. Ice sitting next to an elephant, I don't, because it is, at 0 degrees Celsius completely melts. Then the water, formerly known as ice, is heated up. If the mass of the water is 10 grams, what is the energy required to vaporize all the water? So basically, you have a big old ice cube. Look at that beautiful ice cube. And you want to vaporize it. And so you got to come up with some energies. First, you need to come up with the energy needed to get it from a solid to a liquid. Then you need to account for the energy that as a liquid, it's going to heat up from 0 to 100. Once it hits 100, it's going to undergo another phase change to change from a liquid to a gas. Now, if we kept heating it up beyond that, I would need another delta E to figure out the energy needed to heat up as steam, or if we started below ice, I would need another delta E to figure out the energy needed to start as ice. But the key here is you need to account for all of the energies. The energy needed to heat it up, the energy needed to change its states. And so the equations for this is going to be, okay, this is MLF, this is MC delta T, this is MLV, and that's equal to my total change in energy, which I can't do because I think I'm off the page. Won't let me write. Okay, pulling out my M and now writing delta E since I didn't manage to do that last time. That's just going to give me inside LF plus C delta T plus LV. And now, plugging in values. That's 10 grams. LF, if you recall, is 334 joules per gram, and that's for water. Plus 4.18 joules per gram degrees Celsius. Times 100 is my change in temperature. Plus 2258 for the latent heat of vaporization of water. And when I calculate that, I get 30,100 joules. 100. There we go. Okay,